One of the most straightforward ways to plot a nonlinear relationship is by using a table of values. And that's a table like this, which basically says, well, we're going to have a look at a rule that we want to plot. And we say, if x is a whole range of things, what would y be? So it's a sort of if-then statement. Now, let's have a look at how to do this. We've got a classic nonlinear relationship here. Now, what does nonlinear mean? It means there's curves in it. A linear relationship is a straight line, nonlinear is curvy. And you can tell something's going to be curvy because rather than just having x's and numbers and y's in the formula, it will have x squareds or x cubed or x to the power of 4. So as soon as you see these indices, you need to expect curves. Now, there's a few tricks to plotting these. One is x squared gives the shape of a parabola, which is either a sort of smiley face shape or a frowny face shape. And these things have symmetry down the middle. So if you know where the centre of it is, and you can see what one side looks like, and you start seeing the other side, you can often assume that it continues on like that. Once you have x to the power of 3 or higher, you can't always make that assumption, and so often you need quite a number of x values and their corresponding y values when you're plotting these. Remember, when you're doing a straight line, often you'll only plot, say, 3 points. Technically, you only need 2 for a straight line, and you can join them up, but you normally do 3 in case you've made a mistake somewhere just to check that they're all in line. Now here I'm plotting at least, say, 7 points. Now, what points should you plot? Well, saying what happens when x is 0 is always a nice one to start with, and I've put that right in the middle of my chart because I want to investigate some positive numbers of x, and I've just chosen nice simple numbers, and some negative numbers for x as well. Now, the reason I've done that is because as soon as I've looked at this example, I've thought, what happens when x is 0? Well, 0 squared is 0 times minus 2 is 0. So when x is 0, y is 0. So that tells me that it goes through the origin. And it's giving me a bit of a clue, nothing's been added or subtracted after that, that could be the point of symmetry for the curve. Now, if you're not sure about that yet, that comes with experience. But it's a good idea to always look at some negative and positive values of x. So that's why I've come up with this. All right, next thing to do is just to sub in each of these values of x to see what its corresponding y value would be, and then you can plot those coordinate points. One little trick that can come along is making sure you understand that this one, for example, is minus 2 times x squared. Now that's quite different from minus 2x all squared, and it's also quite different from minus 2x all squared. These three look similar, but they're going to be different. Okay, so what am I getting at here? Well, you need to make sure that you do things in the right order. When you sub x in here, let's say we're saying, what if x is 1? The first thing to do is square it. 1 squared is 1, and then multiply that by minus 2 to get minus 2. Over here, you'd have something quite different. You'd have 1 times 2 is 2. Square that, you get 4. Chuck a negative out the front, you'd have minus 4. So you'd get things wrong if you misinterpret the order of operations over here. All right, when x is 2, 2 squared is 4. Multiply that by negative 2, you get negative 8. 3 squared is 9, times minus 2 is minus 18. Now let's look at the negative numbers that we've put in. Minus 1 squared is also 1. And when you multiply it by negative 2, you get the same answer as what we got here. So it's tempting here to say, well, hold on a minute, my conjecture is that this one might be minus 8 and this one might be minus 18. And it's a good idea just to check. You can never tell if a pattern is a pattern just from one thing. Always just have a good look. And if you made a mistake here after all, and this one wasn't minus 8, it would tell you that this one was a mistake. So it's just good to check it. Minus 2 squared is 4 times minus 2. Sure enough, it is minus 8. And this one will give us minus 18. So we can see that there is symmetry around the middle here. Now, as we go to plot this on the Cartesian plane, there's just a couple of things to take into account. On the y-axis, I need to go from 0 down to minus 18. So I've drawn my x-axis fairly high up on my page. Now, if I'm going to go down to minus 18, one way you could do your scale would be to say, well, let's go down to minus 20. We could go, all right, that's minus 20, so that's minus 10, and then just put in some other placeholders, minus 5, minus 15, and that allows you to quickly and easily work out a scale. Obviously, if you're doing this in your maths book, then the grid paper will certainly help. Okay, I've got a scale there that's going to work. Now, if I use that same scale on the x-axis, 1 is only this big. So I'm going to have 1, 2, 3, minus 1, minus 2, minus 3. And as I plot my points here, 1 goes with minus 2, so we have those two. 2 goes with 8, minus 8, minus 8, and minus 18, minus 18. What we can see here, as I join these up by just drawing in a nice smooth curve, is that it's very long and skinny. Now, this long skinniness is one of the attributes of this curve, and drawing it with the same scale on each axis gives you a really good understanding of that. In effect, this is what that curve really looks like. But you need to be aware that there's another way you can do it, because sometimes you'll see in a textbook question that the scale on each axis might have been done differently. So you want to be aware that that can happen. So if we just grab another colour and plot it a different way, now which one's correct? Well, they're both okay. There's plenty of times where different scales are used on x and y axes. If I'd made this 1, this 2, and this 3, we'd have quite a different scale, something like this. Then it would look a lot fatter and give me a shape much more like this. Okay, now which one's right? Well, they're both right. This one gives you a really good understanding of the actual nature of the curve, comparing x and y values. But this red one is not wrong, and you need to be able to recognise that that's a perfectly valid way of graphing this relationship.